This is the second video in a three-part series on the factorization of quadratics. In the first video, we went over difference of squares, and in this second video, we're going to go over general factoring for simple cases of quadratics. Here we have the quadratic x squared plus 7x plus 10. A couple of things I want you to note right away. For starters, we have this middle term, this bx term, if you will. Because of this, the approaches we went over in the last video will not apply. The next thing I want us to pay attention to is this coefficient for x squared, this a term, if you will. We have no coefficient for x squared, meaning the coefficient is 1. That's significant because the strategy I'm about to show you only works when that a term, that coefficient for x squared, is equal to 1. So for this example, we have a is equal to 1, b is equal to 7, and c is equal to 10. First, we're going to focus on this constant at the end, this 10 or c term. We're going to come up with all the combinations of numbers that multiply to get this 10 value. There's 1 times 10, 2 times 5, -1 times -10, and -2 times -5. Next, we're going to look at the coefficient for this x term, this 7 or b term, if you will. We're going to look at all these sets of factors for 10 that we came up with and determine which combination of these factors add up to 7, that b value. Okay, so first we have 1 and 10. Well, these add up to 11, which is not the same as 7, so this is not what we want. Next we have 2 and 5. Well, these two values do indeed add up to 7, so these are the values that we want because they add up to be equal to that x coefficient. We're going to take this 2 and this 5, and now we're going to move on to the last step of factoring this expression. I'm going to take that positive 2 value and make my first factor x plus positive 2. And I'm going to take the positive 5 value and make my second factor x plus positive 5. And that's pretty much it. This is my final answer. Now, it's always advisable to check our work, so here's how we're going to check our answer. I have x squared plus 7x plus 10, and I factored it to be x plus 2 times x plus 5. Now I'm going to FOIL out this term, so I get x times x, giving me x squared, plus x times positive 5, giving me 5x, plus 2 times x, giving me 2x, plus 2 times positive 5, giving me positive 10. I now collect the like terms, and I get 1x squared plus I have 2x terms, 5x plus 2x for a total of 7x plus 10. Now this expression is the same as the one on the left side, so indeed I did the factorization correctly. Now, to illustrate one of the ways we use this factorization, let's look at a graph of this quadratic. We have y is equal to x squared plus 7x plus 10, where this is our y-axis, and this is our x-axis, and we've got the classic U-shape of the quadratic. The factored form of our expression is x plus 2 times x plus 5, and we know where the x-intercepts are when we solve for when y is equal to 0. Now, for y to be equal to 0, we know that one of these terms has to be 0, because if we multiply by 0, we get 0. From here, we can easily determine that for x plus 2 to be equal to 0, x would have to be -2, and for x plus 5 to be 0, x would have to be -5. And we can see in this corresponding graph that indeed our x-intercepts are when x is equal to -5 and when x is equal to -2. That's pretty much it for this example. We're going to do a couple more quick examples to dial in this process, and then we're going to get into some examples where that a coefficient for that x squared term is not 1, and we're going to have to make some adjustments for that. So here's our next example. I've got 3q cubed minus 3q squared minus 36q. First step to factoring, we're going to factor out the greatest common factor. So if I look at these three terms, I can see that I have 3 that goes into each term here. And also I've got q in each term, the lowest power being 1, so we'll just leave it at q. So factoring 3q out, I get 3q times Now here in this first term I have 3 going into 3 and canceling each other out. And q goes into q cubed, leaving me with q squared. Minus, here the 3's cancel each other out, and q goes into q squared, leaving me with q to the power of 1, or just q. Minus, here the q's cancel each other out, and 36 divided by 3 leaves me with 12. Now I have a quadratic in the form of ax squared plus bx plus c, where I have a is equal to, well, this will be a 1, and b is going to be equal to, this will be negative 1, c is going to be negative 12. Because a is equal to 1, I can use the factoring approach discussed in the last example. So I'm going to start by focusing on this constant, negative 12. The factors that multiply to give me negative 12 are negative 1 times 12, negative 2 times 6, negative 3 times 4. And let's not forget the negative can be the other way around, so I also have 1 times negative 12, 2 times negative 6, and 3 times negative 4. Now I look at this coefficient for x, this negative 1 right here, and want to determine which factors add up to give me that negative 1. As I go down the list, I can quickly eliminate some, but let's pause here at this negative 3 times 4. A lot of people will make the mistake of using this pair, but these total up to plus 1, not negative 1. So this does not work. Instead, it's going to be this last pair, 3 and negative 4, that add up to negative 1, which is what we're looking for. So let's take this pair, 3 and negative 4, and use them for the factorization. Okay, so I have the greatest common factor, 3q, times, here I have x plus 3, as I had a positive 3 value in the pair, and x minus 4, as I had a negative 4 value in that pair. And there's my final answer. Of course, you can do a check on these at the end to validate your answer, but I'll leave that to you. So let's do one more example, and then we'll move to cases where the coefficient for x squared is not 1. Here we have negative 3p squared plus 33p minus 54. First things first, let's look for the greatest common factor. I can see that 3 goes into each term here, but I want this p squared term to have a coefficient of positive 1, not negative 1. So I'm going to take this a step further and factor out negative 3 from all these terms instead. So now I have negative 3 times negative 3 divided by negative 3 cancel each other out, leaving me with 1p squared. 33 divided by negative 3 leaves me with negative 11, so I'm going to have minus 11p here. And negative 54 divided by negative 3 leaves me with positive 18, so I'm going to have plus 18 for this last term. Now I have a quadratic with a is equal to 1, b is equal to negative 11, and c is equal to 18. Let's take this positive 18 and determine its factors. I know that 1 times 18 gives me 18, 2 times 9 gives me 18, and 3 times 6 gives me 18. But none of these pairs will total up to negative 11, as they are all positive values. So let's try giving all of these negative signs, because negative 1 times negative 18 gives me 18, negative 2 times negative 9 gives me 18, and negative 3 times negative 6 gives me 18. Now we can find a pair that total up to negative 11, and I can see that negative 2 and negative 9 add up to negative 11. So using these values in my factorization, I have negative 3 times p minus 3 times p minus 6. And that's my final answer. So hopefully we have a handle on how to factorize quadratics when this a coefficient here is equal to 1. Let's try a few examples where that a coefficient is not 1. Here we have 2x squared plus 7x plus 6. There's no common factor between these terms, so here we have a situation where our a value is going to be 2, our b value is going to be 7, and our c value is going to be 6. This a coefficient for our x squared, in other words, is not going to be 1, and the approach we used in the previous examples is going to have to change. So what we're going to do is we're going to take this a value and this c value and we're going to multiply them. So here we're going to have 2 as our a value times 6 our c value, and we get 12. Similar to what we did in previous examples, we are going to determine the factors that multiply to get to 12. I've got 1 times 12, 2 times 6, 3 times 4, and of course the negatives of these values as well, should we need. Next, we're going to look at this 7 here, this coefficient for x, and see which of these factors add up to get to 7. I can see here that 3 and 4 total up to the 7 here that I'm looking for. So I've got 7 is equal to 3 plus 4. The next thing we're going to do now is rewrite our original expression using this pair of values that we found. So I'm going to rewrite my expression 2x squared plus 7x plus 6 to be 2x squared plus 3x plus 4x plus 6. Now this expression is equivalent to what I had before because we can see that 3x plus 4x total up to the 7x that I had before. It's just written in a different way now. It's going to facilitate this next part that we're going to do. So this next part is what I call factoring by pairing. I'm going to separate these terms into pairs. So now I have 2x squared plus 3x in one pair and 4x plus 6 in another pair. Now that I have these paired off, I'm going to factor the pairs by pulling out their greatest common factor. So for my first pair, I've got a common factor of x. So I get x times 2x squared divided by x leaves me with 2x plus 3x divided by x leaves me with 3. Now this next pair, I've got a common factor of 2. So I've got plus 2 here times now 4x divided by 2 leaves me with 2x, and 6 divided by 2 leaves me with 3. Now what I can see is that I have two terms, each with a common factor 2x plus 3. If I factor that 2x plus 3 out of this entire expression, I can get 2x plus 3. Now let's divide each one of these terms by 2x plus 3. So dividing the first term, I have 2x plus 3 canceling each other out, and I'm left with x. And then in the second term, I've also got 2x plus 3 canceling each other out, and I'm left with 2. Now I have my original expression fully factored as 2x plus 3 times x plus 2. Let's do another couple of examples to solidify this approach. Here I have 21x cubed minus 36x squared minus 12x. First, I'm going to look for common factors, and I can see that each term is divisible by 3 and by x. So factoring out 3x, I'm going to get 3x times 21 divided by 3 leaves me 7, and x cubed divided by x leaves me x squared, minus 36 divided by 3 leaves me with 12, and x squared divided by x leaves me x, minus 12 divided by 3 leaves me 4, and the x's cancel each other out. Now I have a quadratic with my a value equal to 7, my b value negative 12, and my c value negative 4. I'm going to multiply my a and my c values, and I get 7 times negative 4, which gives me negative 28. So I want to find the factors in negative 28 that are going to add up to this b value over here of negative 12. I've got negative 1 times 28. Well, that's not going to work. Negative 2 times 14. Well, that one gives me positive 12, but I want negative 12. So let's make this plus 2 and negative 14. Now I have the combo I need that both multiplies to get me negative 28 and adds up to get me negative 12. Okay, so now let's rewrite this expression using these values. I'm going to ignore this 3x for now and just focus on my quadratic. Okay, so I'm going to get 7x squared plus, now these two terms I've just determined, 2x minus 14x minus 4. And I can see this is equivalent to the 7x squared minus 12x minus 4 that I had before. But now I can factor by pairing. Let's pair off these terms and find the greatest common factor in each. Now, be mindful here. We have a minus 14 here as the first term in the second pair. I want that negative, that minus 14, to stay inside the brackets. So I'm going to put a plus sign between each set of brackets and make sure that negative 14, that negative sign, stays attached to that 14. So now looking at my first pair, I've got a common factor of x. So I can rewrite it as x times, now 7x squared divided by x leaves me 7x, and 2x divided by x leaves me with 2. For my second pair, I've got a common factor of negative 2. So let's write minus 2 over here. So I'm going to rewrite this as minus 2 times negative 14 divided by negative 2 gives me 7x, and negative 4 divided by negative 2 gives me 2. So I've got to recognize here that both terms have a common factor of 7x plus 2. So pulling that out, I've got 7x plus 2 times, I've got an x left over here, and I've got a minus 2 left over here. Now I'm almost done, but not quite. I can't forget the 3x that I've been ignoring all this time. So bringing this all together for my final answer, I've got 3x times 7x plus 2 times x minus 2. Now we've got our final example for this video. I'm going to try to combine a few concepts we've learned. I want to factor the expression 40x to the power of 4 plus 50x squared minus 15. First, let's pull out the greatest common factor. For each term here, the only factor I can see is 5. So factoring out the 5, I get 5 times 40 divided by 5 leaves me 8 times x to the power of 4, plus 50 divided by 5 leaves me 10 times x squared, minus 15 divided by 5 leaves me 3. Now I've got an expression here that is a fourth order polynomial. Our largest exponent here is 4. We haven't factored anything like this yet. But if I look further, I can also see that my exponents are 4 and then 2, and then for this last term I have no x term. What I can do is factor this just like a quadratic by treating this x to the power of 4 like x squared all squared, and this x squared term here like x squared to the power of 1. So when I illustrate it like this, we can see that we've got our first term with the variable with an exponent of 2, and then we've got an exponent of 1, and then a constant. So now I'm going to treat this like the quadratics before and identify my a, b, and c terms. I've got a is equal to 8, b is equal to 10, and c is equal to negative 3. From here I'm going to multiply my a and my c values, and I get 8 times negative 3, which gives me negative 24. Now to find factors for this that add up to positive 10. Okay, I have negative 1 times 24, that's not going to work. Negative 2 times 12, bingo. These two values add up to 10. So now rewriting my expression, I'm just going to ignore the 5 I factored out for now. I get 8x to the power of 4 minus 2x squared plus 12x squared minus 3. Now onward to factoring by pairs. I've got my first pair here. The greatest common factor is 2x squared. So now I have 2x squared times 8x to the power of 4 divided by 2x squared. That's 8 divided by 2 is 4, and x to the power of 4 divided by x squared gives me x squared minus 2x squared divided by 2x squared. They cancel each other out, leaving me with 1. For the next pair, I have a common factor of 3. So now I have 3 times 12x squared divided by 3 leaves me 4x squared, and minus 3 divided by 3 leaves me with minus 1. So I can see that I have a common factor with each of these terms in the form of 4x squared minus 1. factoring that out, I have 4x squared minus 1 times, I'm left with 2x squared here plus a 3 left here. Now, not forgetting the 5 I ignored through this process, I now have 5 times 4x squared minus 1 times 2x squared plus 3. Now I need to recognize here that I still have expressions that have x's with exponents. So I have to examine to see if these should be factored further. Here I have 4x squared minus 1. Well, this is a difference of squares. This first term, 4x squared, the square root of that is 2x. So if I square that, I get 4x squared. And the second term, 1, the square root of that is 1. So factoring this further, I now have 5 times, for my difference of squares, I have one set of brackets with a plus and the other with a minus. The first term is the square root of 4x squared, which is 2x. And the second term is the square root of 1, which is 1. And this last term, now, 2x squared plus 3. Can this be factored further? Well, in the previous video, we also talked about how the addition of squares cannot be factored. So this cannot be factored any further, and so we're going to write it as 2x squared plus 3. There's my final expression. That wraps up this video on general factoring of simple quadratics. The next video on factoring with the quadratic equation will get into quadratics that can't be factored with any of the approaches we've shown thus far.